have one question from the floor. Peter Morrison, thank you so much for the question. So he asks, I'd like to understand more about the trade-offs between the various different types of qubit, superconducting versus trapped ions versus silicon, and so on. Thank you so much, Peter. So I guess this is a very broad question, and throughout this conversation today, we also want to dive into a little bit. But maybe, Joe, do you have some broad commentary, an answer to this question first? And we can go back to Chris and John for deeper dives.
Well, I mean, there's a number of different technologies, and each of them have their own characteristics. There's quite a nice report that came out about a year ago on the threat line that quantum computing poses to cryptography, and it has a pretty good survey from I think 43 or 44 physicists in the field. I think perhaps Chris may have been one of the respondents. I was one of the respondents. There have been quite a few, input from a number of experts from different areas. If you look at how things break down from that, you see that ions and superconducting qubits are generally viewed as the nearest term bets. As the most likely to succeed in the near term, and those are quite different technologies. There's some very nice things about ions in particular. They are optically active often, which means you can get photons out. You can, in principle, think about entangling devices at a distance, using them as part of a quantum network, as well as computers in their own right. They're also extremely good at storing information for long periods of time. John, I believe, has also the record for perhaps the longest lived qubit to date, right, for storing quantum information in silicon.
No, John, you don't have to be humble, and you're muted.
Well, look, I mean, maybe in the solid state, but ions, I wouldn't like to measure qubit lifetimes against ions.
Okay.
Yeah, it's certainly for solid state devices that may be true.
So there's different properties to each of the devices. There's different timescales for the interaction between qubits. There's different levels of decoherence, and there's different levels of control. Optics, photonic qubits are special in their own right because photons don't really interact with one another. So there's no easy way to do entangling gates with them. For those, you need to make all of your entangling operations through projective measurements. So you need to set up some measurement that projects your system into an entangled state rather than being able to just interact two qubits. So each system has its own pros and cons. At this stage, I would say it's probably not clear yet who's going to get there first. Although I'm sure our guests have their own views on that and what will take the lead.
John.
Look, I mean, I think of course, it's very difficult to boil down, this very the complex parameters that Joe's mentioned. When assessing these platforms, people are trying to look for a magic number, like the number of megapixels in a camera, to say, to measure each one, and there've been various attempts at this. Obviously, sometimes people talk about qubit numbers. Look how many qubits are in my processor. But that we've already talked about errors and how important it is to keep the error very low, so the quality of each operation is very high. But each of those numbers on their own doesn't tell the full story, and there've been attempts to try to look at combinations of those. I think in terms of assessing quantum processors, the sort of prototype processors as they are today, it's really about algorithms. Picking different classes of algorithms and seeing how complex a problem can it solve. But if you're then trying to make predictions about which one is going to, and that's just trying to work out which processor we have today is more powerful. If you're then trying to work out which one is going to be most useful in the future, that becomes very difficult. You have to look at different ways to measure scalability. The networking, the optical link aspect of ion traps is very nice. So the networkability is important. Integration, and most probably, my own view is that there will probably be different waves of dominant platform. We had the first computing devices were mechanical, right? They were gears. We had computers. The first real computers, general purpose ones, were based on vacuum tubes, and now it's predominantly silicon. So I think there's every reason that you will have different forms of quantum computing hardware at different stages in their development.